This is Shakil Ahmed. In this video, we will discuss assumptions of linear regression. When we are using linear regression for data analysis, we often apply without checking the basic assumptions of a linear regression. Basically, we need to first confirm whether the assumptions of linear regression are satisfied or not. So there are some basic assumptions we need to check before going to the analysis of our data. The first one is the linearity assumption that the axes are linearly dependent on uh, y is linearly dependent on axis. There is a linear relationship between y and axis. If we have multiple axes, then all the axes should have linearly related to y. And the second is the independence assumption. Independence means we have selected data uh, independently as the pair of yi and xi are independent of yj and xj with their previous value or with the other observation in the data. So it is called the uncorrelated assumption of the error term. The error term is independently distributed. And the second is the error term is identically distributed. That is homoscedasticity. That is homostochastic condition. We should have a constant variance. That is called the identical error term. And the third one is a normal distribution of the residual. That is important while drawing inference, as we need to apply t-test or z-test, then those tests are dependent on the normality of the error term. So we need to confirm this first. And then multicollinearity, there should be no strong linear relationship between the two variables. Although uh, a little relationship is okay, but there should be no strong relationship between the covariates or independent variables. And there should be no outlier in the data. If there is an outlier or the data is skewed, then we can't proceed with the linear regression. So we see different diagnostic methods. Uh, we can create scatter plot to see whether there is a linear relationship or not. And for independence, we apply the Darwin-Watson test. And for homoscedasticity, we check using the residuals versus the fitted values. If the residuals have some pattern, then we can say that there is a heteroscedasticity in the data. And then normality of residuals, we can check using a QQ plot. We also test the normality using the square wheel test. And then multicollinearity, that is assessed using a variance inflation factor, and the outlier is detected using the Cook's distance method. So we will discuss all these in brief using R. We have a data on heart disease, and we just import the data, and you can see this summary. We have different mixture of variables, qualitative as well as quantitative variables. And if we want to assess the relationship between the resting blood pressure and the maximum heart rate, how the resting blood pressure is affecting the maximum heart rate. So we just see using a scatter plot whether there is a linear relationship between these two variables or not. So what this is a GG plot with the X resting blood pressure and Y maximum heart rate, and we are just making a scatter plot with the fitted linear model. Sorry, we need to very GG plot and then we can run. You can see, is there any linear relationship? I don't see a linear relationship, although there is no relationship between the two variables. The relationship is not significant, as we can see with the plot. This is just a shape of circle. If there is some elliptical shape of the residual of these dots, then we can say that there is a relationship, might be positive or negative, but in this case, we see no relationship between the resting blood pressure and maximum heart rate. So then we can see the whether the error terms for this regression, for example, is independent or not. We use Durbin-Watson test, and you can install the LM test, linear model test. Within linear model test, we first uh, run the model, simple linear regression model for resting blood pressure, maximum heart rate on resting blood pressure, and then we perform the Durbin-Watson test. The Durbin-Watson test is just DW test, and then write the model which you want to diagnose. And you can see the Durbin-Watson statistic is 1.67 with a p-value 0.0009. It means there is some autocorrelation. As alternative hypothesis, true autocorrelation is greater than zero. So here p-value is small. It means the H naught is rejected. So we can see there is some autocorrelation, uh, as the true autocorrelation is greater than zero. So a non-significant value of p-value is always recommended. Then we can check the uh, basically the range should be between 0 and 4, and uh, closer to 2 suggests that no significant autocorrelation, although it is uh, near to 2, but the p-value is still significant, as I think the standard error is very small. That's why it's showing a significant relationship, significant autocorrelation. Although the Darwin-Watson statistics is nearly close to 2, now that is a sign of no significant correlation. And then we can check the homostasity. So for homostasity, we can perform the we can find the residual analysis. Is basically we just see the residuals over the fitted values. We can just do the residual analysis where we can find 4 plots. If we just use the plot the model, you will get 4 different models. So I'm using the power function to keep all the plots on the same page and just run this. Although you can run the QQ normal and QQ line to test the normality, we will do later. But first we see is there any heteroscedasticity or not. So here you can see different types of plots. Uh, the first one is the fitted versus the residuals. If the values are more close to this line, this is not clearly showing, as the screen is not much larger. You can see these points are plotting on in the form of a circle. So we can say there is, uh, although there is no uh, linear relationship between y and axis, but we can say that the error term does not depend on the fitted values. If there is a pattern with the fitted values of the residual with the fitted values, then we can say that there is a heteroscedasticity. If we can see, for example, such type of with dispersed and then close to this point, dots are plotted in such a way, then we can say that there is a heteroscedasticity. But in this case, we don't see any heteroscedasticity. And then you will get the QQ plot, which tells the normality. Although you can plot separately the residual, this will be the same code for this plot. And if the plot is if the dots are plotted on the near to the 45-degree line, we can say that the data is normal. It's slightly deviated from normality. And then we can for this plot gives the fitted versus standardized residuals. And what this plot suggests, uh, this plot again suggests the heteroscedasticity, as the residuals are plotting on the y-axis and the fitted values are plotted here. And this plot tells us the uh, influential observations, as if the most of the values are plotted on this side, these are the leverage value that are more deviated from their residuals are more deviated from their true mean. So if the values are plotted on the right side, we can say that these are the influential observations. And you can also apply the Cook's test to see which observations are outlying and which observations are not. You can check the influential observations using the Cook's distance method, and uh, we just see the Cook distance of the model. It will give different values, influential values. You can see these are the distances, and comparing the distances with the threshold. This is the threshold 3 divided by length of this variable basically, and this is number of observations. This is the threshold, and we are comparing if uh, influential value is Cook's distance is greater than the threshold, then we say that the observation is influential. So you can just check which observations are influential. These observations are influential observations in your data set. And you can see these through a plot. You can plot the heart rate and the uh, maximum heart rate and resting blood pressure. This is just the scatter plot, and we can plot the influential observations on the plot. These yellow colors dot with yellow color uh, showing the influential observations. These are the influential observations. And the last thing is the multicollinearity. The multicollinearity is checked using the variance inflation value, VIF value, and we are this is for multiple linear regression when we have different regressors. I'm adding age and the resting blood pressure and cholesterol, and the data is the heart data. And for this, we need the library call, and then check the VIF value. So these are the variance inflation value for these variables. If the variance inflation value is greater than 10 or even 5, we can say that there is a relationship between two variables. There is some correlation between the variables. So variance inflation factor is this variable is not causing any multicollinearity. This variable also causing any multicollinearity. So this model is appropriate as these variables are not related to age. Basically, when we uh, are doing the ex- different exposures on the disease outcome, then most of the variables are mostly related to the age. Then we need to check for whether there is a high correlation between the age and the disease, and that may cause inflation in variance. And alternatively, the test statistic will be insignificant, and your result will be not that good. And in that case, if you have highly correlated variables, then you need to go for partial least square, or you can use the rigid regression method if you have high number of variables. So there are some solutions when you have high variance inflation, and the variables are highly correlated. So before applying a linear regression, you must check for all these assumptions, and then uh, apply the. And if these assumptions are not fulfilled, then you have alternate solutions. If the linearity assumption is not met, then you may go for some certain transformation, or you may go for some nonlinear or polynomial regression, or you need to include the interaction terms as well. And if there is uh, multicollinearity, then you have the solutions as I already mentioned. And if there is autocorrelation, then you need to go for first difference or second difference, and you need to go for time series, deal with the time series data uh, methods used for time series data sets. And if you have heteroscedasticity issue, then you can go for weighted least square. You can include your the variance. Basically, variance is different for different observation. Then you can use weighted uh, estimates instead of simple estimates. So always, whenever applying some regression method, the linear regression method, you need to check the assumptions, and then uh, go for the uh, final results. Thank you for watching.